Hey guys, good evening. How are we? Everybody's good? You guys hear me? Can just type in the comment section for me. Evening, Jailer Francis. How are you? Welcome to HTS Online Marathon. Waiting on the others to get here. All right, guys, remember to share the link with your classmates, your friends, enemies if you have any. All right, promise to be a massive one. Let's go. So 2 minutes more, and then we can kickstart. All right, so for those wondering what we'll be doing today, we'll be doing May, June. That's the May, June. Everyone can see the whiteboard. So I'm going from my whiteboard. So we're doing May, June 2014. May, June. All right, promise to be a massive one. Let's go. 2014. 2 minutes more. All right, so for those wondering what we're doing today, all right, guys. We're on the 2014 paper, right? And I will be using my whiteboard today to actually go through the questions here. I hope that we're all seeing the questions. So it's May, June 2014. Everybody seen it? Just confirm for me. Let me look in the chat. All right. All right, good. All right, so let's go. So the question says, the first question that we have, it says the heat of neutralization can be determined by measuring the temperature change when various volumes of acid are reacted with a base. Experiment 1 was carried out to determine the heat of neutralization for the reaction between potassium hydroxide and dilute HCl. Portions of 0.1 molar HCl 0.1 molar HCl were added to 25 centimeter cube of aqueous potassium hydroxide in a plastic cup and stirred. The highest temperature reached after each addition was recorded, and the results obtained are presented in table 1. So let's now look at table 1, right? So the first thing, guys, that we need to understand is that once we're doing CSEC chemistry paper, the first question that we normally have is an experiment question, right? So let's write that down. So the first question that we normally get is an experiment-based question. Now, the experiment-based question can be drawn from a lab. It can be titration, it can be qualitative analysis, it can be quantitative analysis, you name it, right? Luckily, in this one in 2014, they gave us a titration form of question. Now, let's look. So they gave us the volume of HCl, and they also gave us the temperature of the mixture. So this is actually an energetics kind of lab, heat of neutralization. Of course, it's when an acid and a base reacts to form salt and water. And what you're going to do is actually using your equation from energetics, that is Q equal mc delta T, to actually solve. All right, let's go. Let's take a look at the table just a bit. So I'm giving you about a minute to analyze the table. All right, so let's go now, guys. So the first question, it says, let's go. It says, use the data from table 1 to plot a graph of temperature against volume of acid, right? So it's temperature against volume of acid using the axis provided in figure 1. So what we're going to do now is to scroll to figure 1. So let's scroll to figure 1, right? Right? So it's a graph here. So as you can see here, the volume of HCl, so let me stop sharing my screen so we can work it together. The volume of HCl is on the x-axis, while on the y-axis here, what we have is the temperature, right? Most of 3 points would have already been plotted for us. Let's look. So it's 2 points. So 1 and 2 here, that's plotted, right? So let's now take a look at our data points. All right, let's take a look at our data points. Now, what I'm going to do, I'm actually going to mimic the graph. That is to say, right? That is to say, I'm not necessarily going to draw the graph accurately, but also more so a rough estimate. So you can actually get an idea of what you should have. All right, so let me just write this down quickly. So volume of HCl, 0, 5, 10, 15, 20, 25. This corresponds to 27, 29, 31. All right, so I have 0, 5, 10, 15, 20, 25, 27, 29, 31, 34, 36, 38, right? Will score at 30 centimeter cubes. We have 36 temperature, right? 35 volume, which corresponds to a 33 temperature. Now, based on this plot, so I want you guys to now pay attention to my whiteboard here, right? So this is the volume of HCl 0, 5, 10, 15, 20, 25, 30 to 35 centimeter cubes. And these are the corresponding temperatures. Now, let's just analyze the graph, guys. What you would have realized is that as temperature, as the volume increases, temperature increases. Let's just explain the graph so we can understand fully. Remember that this is a neutralization reaction, right? In which you're now adding HCl, so it's a reaction with potassium hydroxide KOH, reacting with HCl, and this is going to form potassium chloride, KCl, plus water. Now, as you add more HCl, right, the greater the reaction. So because the greater the reaction in itself becomes more exothermic. So what you realize is there's a temperature increase. Now, as temperature increases, it reaches at a point which would call or denote by the neutralization point, which is normally our highest point on the graph. Now, once it reaches at this point, which is our highest temperature, the 38 degrees C, it now falls back down to 33, right? Let's go ahead now and plot our graph, shall we? All right, good. Let's go and plot our graph now. So plotting our graph, right, would actually have our x-axis. That is temperature against, of course, the volume of HCl, which is here, volume of HCl. And the volume of HCl is 0, 5, 10, 15, 20, 25, 30, and 35, right? And of course, on the y-axis, based on the plot, it's from 20 to 40, right? So it's looking at 20, 22, 24, right? 26, 28, right? That's 30, 32, 34, 36, 38, right? And 40 will be up here. Remember, it's a rough estimate. All right, so let's go now. So as we know, at 0 centimeter cube, this would correspond to 27, meaning that when we would have added a volume of 0, meaning no, we add 0 centimeter cube of HCl. So there's no HCl, it's the initial concentration, or it's the initial point of the start of the experiment. So at 0, this corresponds to about 26, which would be about somewhere here, right? With addition of 5 centimeter cube, we're at about 29 centimeter cubes, which will be here, right? Addition of 10, we're at about 31, which will be here. Addition of 15 centimeter cube now, guys, we're at where? We're at 34, which would be somewhere here, right? Addition of 20 centimeter cubes, we are actually at 36, which is up here, right? 25 will bring us to 38, which is also up here, right? Sorry for going so far, right? And then at 25, we go back down to 36, and at 30, back down to 33. So basically, our graph would look something like this here, right? In which the reaction starts, right, at a low temperature, because you would have added 0 centimeter cube of HCl. But as you start now, guys, to add more HCl, right, the reaction increases in terms of the temperature increases because there's greater reaction. Now, at this point, the neutralization point, it's an indicator to us that most of the HCl and the potassium hydroxide would have used up. So the reaction is neutralized. It's basically ending. And then now there's a decrease in the slope. And that's how we do our neutralization graph. Everybody following that? Let me know. All right. Any comments? Let me check the comments. Give me a second here. All right, so I see where Akila says, sir, who did the 9 be on the y-axis? What 9 is that, Akila? Let me check back on the question so we can actually discuss that one. Let me see what you're talking about here now, Akila. Or the 9. What 9? I'm not seeing a 9. No, man. On the y-axis, what 9 are you talking about? Remember, you know, Alkelia, that you're plotting what? You're plotting the temperature against the volume. So all of the data points for temperature would be on your y-axis, while all of the data points for your volume would be on your x-axis. All right? Let's move on. So I'm sharing my screen back. Let's move on. So we get the first one out the way, which is plotting the graph. So that's 4 marks though. So everybody put that in them back now. So 4 marks, get that out the way. Remember, your first question on the exam paper is normally a practical question. Get that one out the way. Let's move on now. We're going to the second question. Let's go now. So it says from the graph AI, right? Determine the volume of acid required to neutralize 25 centimeter cubes of potassium hydroxide. So let's look again. It says from the graph, determine the volume, right? Determine the volume of acid required to neutralize 25 centimeter cube of acid. All right, how do you do this one? Think about it. How do we do this one? Anybody know? How do we go by doing this? Well, this is quite simple. One of the ways in which we could actually do this is considering that, first of all, it's a 1-to-1 mole ratio, right? So essentially, and we can also use the graph in itself to also determine as well the volume of acid that would be required to neutralize that 25 centimeter cube of potassium hydroxide. Now, the volume of acid that would also need to neutralize that 25 centimeter cube of potassium hydroxide is also 25 centimeter cubes, right? Because let's look on the reaction. So it's KOH reacting with HCl, and that's forming KCl plus KOH. It's a 1-to-1 mole ratio, if you realize, right? So pretty much the same equivalent volume would just be the same, or remains the same. Let me stop share so you can see my board. So if you look, right, so it's KOH reacting with HCl to give KCl plus KOH, right? It's a 1-to-1 mole ratio. So because it's a 1-to-1 mole ratio, the same volume that is used, right, it would basically be the same equivalent volume that it would take to neutralize it. Simple as that. All right, so it's 25 just the same. All right, let's continue. All right, next question. It says determine the temperature difference during the reaction. So it says determine the temperature difference during the reaction. How do we do this one? Determining the temperature difference. This is quite simple, guys. Now, determining the temperature difference, delta T, remember that delta T is equal to what? Tf minus Ti. That is, it's the final temperature minus the initial temperature. Normally, the final temperature is not necessarily the end temperature, but it's the highest temperature reached. So Tf here represents final temperature, right? While Ti would represent your initial temperature. Now, if you look on the graph, and you're supposed to remember based on, let's just look, for those who don't remember the data points, so let's just look, looking at the data points, right? The data points here would have shown that 38 is the highest temperature reached, right? While the initial temperature was 27. That means then that our T, delta T, is basically 38 minus 27, and that gives us what? 11 degrees Celsius. So that is 11 degrees Celsius. All right? Everybody following so far, so good? Let me know. All right, going back to the graph. Well, back to the paper, my bad. All right, so going back to the paper. Let's see the next question that they asked us. All right, let's look at the next question that they asked us. So they said determine the temperature difference during the reaction that we just did, right? Which is II. Do we have an IV? Good. So we do have an IV. Let's go to that IV. All right, so IV says calculate the heat change, right, at the point of neutralization for the reaction, given that the specific heat capacity of the solution is 4.2 kilojoule per kilogram per degree Celsius, assuming then that the density of the solution is 1 gram per centimeter cube. How would we do this one? Let's go, shall we? All right, let's go. All right, good. Let's stop share. All right, before I even stop sharing, I want to discuss something to you. All right? Let's look carefully now, guys. So delta H, right, is equal to what? MC delta T, where M is the mass of the solution. Now, at the neutralization point, if you're supposed to remember the graph, at neutralization point, where the temperature was 38, the corresponding volume was 25 centimeter cubes. Now, because it's, of course, an heat of neutralization reaction, which takes into account the addition of an acid and a base to form salt and water, right? Then we must account for the overall mass of both acid and base. We make an assumption. The assumption that we make is that 1 centimeter cube, right, is really equal to 1 gram. It therefore means then that because at the neutralization point of 38 degrees Celsius, where the volume was 25, meaning that the neutralization volume, or what we call the equivalence volume, is 25 centimeter cube, right? Therefore, the overall mass of the solution, right, will be 25 for the acid plus the 25 for the potassium hydroxide, which is 50 centimeter cubes. That, right? There goes our M, because we would have assumed that 1 centimeter cube is equal to 1 gram. Therefore, 50 centimeter cube ideally is 50 grams. Everybody good so far? So therefore, we can go ahead and work and say, okay, delta H then is equal to 50, right, times C, where C is our specific heat capacity, which is 4.2, right, joule per kilogram per Kelvin, times delta T, which is the temperature difference. What's that temperature difference now, guys? That's 38 minus or 27, right, which was 11, right? Everybody good so far? So that's times 11. Now, remember that this, however, right, is 50 grams, and they would have given us this here, the 4.2, right, in kilograms. So we can just divide by 1,000 to get it in kilograms. So that will be 50 divided by 1,000, 0.05 times 4.2 times 11. Take out the calculator for me. So it's 0.05 times 4.2 times 11. What do we get? All right, give you some time. So that's 2.31. That's what I get, 2.31 kilojoules. Let me know if that's what everybody get. Let me know. Everybody got the 2.31 kilojoules? Let me see what's going on in the chat. Repeat for question 2. The formula. Okay, all right. Let's go with that again. Amanda said we should repeat. So the formula, Amanda, right? It's delta H is equal to MC delta T, something that you learn in physics, or Q equal MC delta T, where M represents the mass, right? C represents the specific heat capacity, and delta T is actually the temperature. As I was saying, M is the overall mass of the solution. That mass would have to take into consideration the mass of HCl as well as the mass of the potassium hydroxide. So that's 50, that would be 25 plus another 25, which is 50. C is a specific heat capacity, which is 4.2, right? And delta T is 11. However, as I was saying, it's 50 grams, but they gave us 4.2 kilojoules, right, per kilogram per degree C. So we have to convert the 50 grams into kg by dividing by 1,000, and we get 0.05. So to be 0.05 times the 4.2 times 11, and we get 2.31. Right? This is energetics. So this is on the module 1, energetics. Everybody get that? All right, so I just realized that I was actually muted. All right, so let's go again. So it's B. So it says Sam conducted a series of experiments, right, to investigate the effects of the various factors of the rate of reaction between magnesium and iron chloride. 2 5 cm cube or 2 5 centimeter strips of magnesium ribbon was measured. One of the strips was further cut into 1 cm strips, and also it was placed into a 100 centimeter cube of iron chloride solution. The other 5 centimeter cube or 5 cm strip, right, was placed into an equal volume of iron chloride solution. Figure 2, right, it shows reactants that were used to investigate the effect of one factor of the rate of reaction at the start and the end of at the 30 centimeter cube, 30 seconds, my bad. All right, so let's look on the experiment. So we're looking on 2 experiments, experiment 1 and experiment 2. So let's look what's taking place in experiment 1. So as you can see here in experiment 1, we have the 5 cm strip, right, in the 1 molar FeCl3, right, as opposed to just one long 5 cm strip. So in beaker A, you'll realize that the strips, guys, is now in smaller pieces. So rather than having a long 5 cm cube strip, you actually have different strips, all measuring 1 cm, right? And the beaker, of course, the appearance of it at 30 seconds. All right, let's move on and go to the question. All right, so the first question says, it says, suggest a suitable aim for this experiment. What are we looking at? So this is still a lab question. What are we looking at? Let me hear some suggestions. A suitable aim for this experiment. What we're really doing, guys, is to investigate the rate of reaction between magnesium ribbon, right, and iron trichloride using different surface area. Because ideally, let me stop sharing so we can demonstrate on the board. Because ideally, what we're doing, when we have this, if we're supposed to have this block, and it measures 10 centimeters, and then we try to split up the blocks into 10 different blocks, all measuring 1 centimeters. What we're doing ideally now, students, is that we're now increasing the surface area. And as we know, as we increase surface area, there's an increase in the rate of reaction. So therefore, we can justify and say then that the title of this lab can say that, right, to investigate the effect of surface area, right, on the rate of reaction of magnesium ribbon when reacting with iron trichloride. Everybody following? Let me know. All right, going back. All right, so we're going again. It says, describe, next question. It says, describe what will happen, right, to the contents of beaker A after 30 seconds. Let's look. So what would take place in beaker A, right, after 30 seconds? Remember that, of course, the magnesium ribbon is in beaker A. Let's just take back a look on beaker A. So as you can see, the ribbon is there, right? And you have the 1 molar FeCl3. All right, so let's go on the whiteboard and then let us explain. Now, remember the reactivity series. It says, please send cows, monkeys. Please send cows, monkeys, and zebras in 2, right, large, heavy cases marked, stamp, goods, Persian. Using the reactivity series though, guys, you would have realized that magnesium is way more reactive than iron. So what is going to take place in beaker A, you're going to have displacement reaction. So it's really a displacement. That is to say, when magnesium reacts with the FeCl3, the magnesium, because it is iron reactivity series than iron, would displace now the iron from the from the chlorine, or from the chloride rather. So you end up with magnesium chloride and ions, Fe3 plus ions in solution. So let's go. So the reaction taking place in beaker A is, of course, a displacement reaction, right? So it's a displacement reaction because the magnesium ribbon is more reactive than the iron, right? So the magnesium will displace iron, right? And of course, what you would have iron here, right, being deposited on the bottom of the beaker. Iron 3 is actually red in color, right? So you'll actually have deposits of iron 3 on the bottom of the beaker. Everybody get that? We'll explain. All following me? All right, so let us go. Let's continue our question. Let's continue again. So part 3, it says write a suitable ionic equation, right, for the reaction. Anybody know how to write an ionic equation, everybody? Want to know how to write an ionic equation? All right, let's go. Let's stop share and go back to the whiteboard. So it's of course a reaction of magnesium. Don't forget the state symbol. So it's magnesium, right? Solid state. That's the state symbol, right? And it's reacting with iron chloride. It's iron 3 chloride, right? What's the state symbol for iron chloride? All chlorides are soluble except, what is it? Except lead, right? Silver chloride. Good. So this, of course, is aqueous. Reaction magnesium plus the iron chloride. So you get Mg, right? Cl2, which is also aqueous, right? And of course, you get the iron, the Fe. Let's balance the equation. That's the next step that we need to do. Let's balance the equation. So I have 3 chlorine here, right? We can actually put a 3 here and put a 2 here. So to balance the chlorine, so 2 times 3 is 6. So that is balanced. That's 3 magnesium. So we also need a 3 here, right? That's 2 Fe. So we need a 2 on this side, just the same. All right. What we normally do in ionic equations, let's go now. Let's break it down. So magnesium, it remains as is, right? So no need to split or anything, right? It's in its natural state, magnesium, right? Of course, plus FeCl3. Remember that in ionic equation, we're now supposed to split up the ionic compounds. So it will be 2Fe plus, 2Fe3 plus, right? Plus 2Cl plus 3, my bad. Well, plus 6 actually. Because that's 2 times 3, which is 6. Right, so it's 2Fe3 plus 6 Cl minus aqueous, right? This is also aqueous, so we're actually splitting the ions, right? And this is gonna give, let's look, Mg, so it's 3Mg, 2 plus, the charge on it, right? And this is 6 again, 6 Cl minus aqueous, right? And that is Fe plus 2 Fe, and that is in solid state, of course. Next step is to what? We need to what? Remove our spectator ions. What are spectator ions? It's any species that remains chemically unchanged on either side of the equation. That is, their state symbol remains the same. So iron state symbol remains the same. No, not iron. So we can't rub that out. Chlorine, let's look. Chlorine, yep. It's aqueous here. It's also aqueous here, right? That now leaves us with 3Mg solid plus 2Fe3 plus aqueous to give 3Mg 2 plus 2Fe solid. And that's our ionic equation. Everybody get that? Let me know. All right, looking good so far. Remember to share the live, to subscribe to the channel. I hope you guys are learning and we're enjoying so far. All right, we're gonna move on now to our next question. All right, next question on the paper. Let's go. So it says, how would the contents of beaker B differ from the contents of beaker A after each is left for 30 seconds? So let's analyze that one. So this is a case where it's actually working on our reasoning ability. So it says, how would the contents be different? What do you think about it? What do you think about it? Let's think carefully. All right. So if you remember, in beaker A, right? Beaker A would have the strips that are now divided, right? So it's a greater surface area. Now, because it's a greater surface area, oxidation will take place more rapidly. So what you realize is that now, guys, is that the contents in beaker A, right, will now change to a lighter yellow color, right? Because it's now reducing to the Fe2 plus ion, which is normally yellow-green, because the reaction is much faster. So in beaker A, right, in beaker A, what we're saying is that the red-brown color that was there, right, is gonna get light over time because of oxidation. Remember that oxidation is influenced by oxygen. If you have it in the air, of course, oxygen will react and cause a reduction to occur, redox reaction. Remember that, right? So in beaker A, it's gonna change to a lighter yellow color than in beaker B, right? That's simply, right? And we can even go on further why that is, because it said explain your answer in IB why we say that. Remember now, guys, that in beaker A, we have finely divided chips, right? We have finely divided chips. The finer the chips are, guys, it means then that the surface area on a whole is greater. Now, if we have a greater surface area on magnesium ribbon, it means then that more molecules of magnesium are now exposed to the reaction. Therefore, the greater the surface area, the greater the rate of reaction, the greater the displacement will actually be, right? And faster the overall reaction, as opposed to the long strip in beaker B. I hope everybody getting that. So far, so good. Let me pause a bit and check the chats. Good, good. Enjoying the live. That's good, Roger. You think you lost? Why you lost, Amanda? Talk to me. Let me pause a bit. Text it in the chat. We don't want to leave anyone behind. Talk to me, Amanda. Why you lost? Why you lost, Amanda? Text it. Let me hear why you lost so I can help you out. Anything from Amanda? Nothing as yet? Message. All right, not seen. Let me just check on some classes here. Let's check. All right, so moving on. I'm not seeing anything from Amanda, so moving on. All right, let's go back to it. So explain our answer there. Let's move on to question C, right? So it says some students was required, right, to determine whether an unknown substance contained the sulfite ion, right? And figure 3 shows the arrangement of the apparatus for the procedure used to carry out the test. So we have dilute HCl or dilute acid, right? Not sure if it's HCl. So it's dilute acid plus sulfite, and we have a solution Y. And it said identify solution Y. So let's go and read the question once more. So it said some students were required to determine whether an unknown substance contained sulfite ion, right, or not. All right. So what does this mean now, guys? So we have one beaker over this side and this side that contains our sulfite ions. And then we have another beaker on this side that contains our solution Y, right? So we know definitively that it's sulfite. But what do we know about sulfite? Now, we could actually test this, right, based on redox reaction. And let me explain why we can test this based on redox reaction. Now, if you remember, SO2, right, and SO3 minus here, and rather sulfur dioxide is a known oxidizing agent, is a known oxidant, whilst potassium permanganate is a known reducing agent. It therefore means then that solution Y, we could, based on the setup of the experiment, then solution Y, seeing that the experiment is to test whether or not sulfite is there, then obviously it could be on the basis then that solution Y is a reducing agent, considering that we already know that the SO2 and the SO3 minus is of course oxidant and it's an oxidizing agent. So we are going to assume and name any reducing agent, whether it may be potassium dichromate, K2Cr2O7, right? Or potassium permanganate, KMnO4. So it could be any one of these, any known reducing agent. Following? All right, let's go. I'm enjoying this live. I'm enjoying. I hope you guys are enjoying just the same. Remember, if you don't understand, comment. Let's go now. Let's continue. It says, with reference to solution Y identified above, explain the changes that we now observe in class 2, right? If the unknown substance contains sulfide ion. So it says the expected changes. Of course, we all know this. We don't live under a rock and we're chemists, right? So how would we know then what would be the expected change in experiment in class 2? Now, if it is potassium dichromate, right? Of course, it will change from orange to green. Remember, potassium dichromate will change from orange to green, primarily because it's changing from the Cr2O7 2 minus to Cr3 plus. That's all, right? Whilst if it is potassium permanganate, right, what is going to take place? It's going to change from purple to colorless. That is MnO4 minus to Mn2 plus. So that is our expected change. All right, everybody get that? An explanation. I'm going to explain it now to you guys. Let's look. Stop share. All right, so let's go. Let me explain what's actually taking place here. Now, when dilute acid, guys, reacts with sulfite, right? Sulfur dioxide gas is produced. So if we're supposed to have HCl reacting with a sulfite, SO3, right? Then it's gonna give off SO2, the gas SO2. And as we know, right, the gases are, oh, I did say that the gases are, my bad. I didn't say that the gas is a oxidizing agent, my bad. It's a reducing agent. I think I might would have made a mistake there. So the gases are reducing agent, my apologies, all right? So the gas, of course, the SO2 is a reducing agent and it will reduce, let us use the potassium permanganate. It will reduce the potassium permanganate or the potassium dichromate. That is to say, let's look on the reaction. So we have MnO4 minus, right? And that is reacting with the sulfur dioxide, the SO2, right? And that's gonna form first SO4 2 minus sulfate here. And at the same time, you're gonna also get manganese sulfate, which is Mn, SO4 2 minus, plus Mn, SO4, right? Plus sulfuric acid. That's the reaction. You don't necessarily need to write this extensive reaction doing it, right? All you could do to explain is that the SO2 will change the MnO4 minus to Mn2 plus. Whilst if it is Cr2O7, it will change from Cr2O7 2 minus to Cr3 plus. This is just an extensive reaction, right? But this is a shortened version that you can use, especially at your level. All right, good. Let's continue. All right, so it says, how do you modify, let's look now. It says, how do you modify the experiment to confirm the presence of carbonate instead of sulfite? Let's look. How do you modify the experiment? This is simple. Carbonate. How do we normally test for carbonate? Now, carbonate, guys, it would actually give off carbon dioxide. So you remember that thing that we said form a milky precipitate? That's how you normally see it, right? Now, what we can do, remember that the experiment will set up like this, in which you have one solution containing the sulfite, right? You have another containing solution Y. So all we need to do then is to now change solution Y to calcium hydroxide. Because remember, when carbonates reacts with calcium hydroxide, right, it's gonna form calcium carbonate and also give off carbon dioxide, right? And you're gonna form a milky white precipitate. All right? Pretty much that's so. All right, so that's our first question, 25 marks. How do we feel about that question? Our first 25 marks. We feel like we get the 23 out of the 25. We feel like we get the 25 out of the 25. Because here at HTS, my students, they aim to get 23 out of 25, not less. What do you feel like you will get now? Talk to me. Talk to me, guys. Let's see what's going on in the chat. Okay. You lost from it. Okay, all right. Let's see what's going on. Everybody good? So far, we're understanding all the live. Thumbs up if you're enjoying the live. Remember to share, like, subscribe. If you want to be a part of our sessions, 202-6446, massive, right? We produce excellent results, as said before. More than just grade ones, Caribbean Awards, you name it. Let's see what's going on in the chat before we go on to question 2. All right. Let's go back to the sharing. Right now, going to question 2. So finish question 1. We're confident that we'll get 25 out of 25. You see some person said they get 19. Right? Some person said they get 10. Why you get 10, Delano? Join the session if you get 10. Call us, make money, make daddy call us. If you feel like you get 10, not less than 23. Peter said, good night, all. You're just coming on. All right, good. Moving on now to question 2. Now, your first question is normally a stable question. That is, it's normally from a lab, right? And your question 2 is normally fluctuates. It depends on what they want to be. Now, this year at question 2, it focuses on periodic table and periodicity, right? It's coming again from section 1, but more so focusing on periodic table and periodicity. Oh, that we are familiar with the question. Well, with this topic, that I should say. All right, let's go. Says this is periodic table and periodicity. And why we do this? Says a case in which we use our reasoning ability, using certain trends that we know and see what we can get for our unknown. Yeah, man, for unknown. So let's look on this question. It says the position of three unknown elements, X, Q, and V. Wow, Z, not V. I'm moving too fast. You see? All right, let's go. So the position of three unknown elements, X, Q, and Z, are shown in the periodic table. Right? It says, based on the position of element X, state whether it should or it would react more vigorously or less vigorously than water than K would react. Let's say analyze this. Firstly, you have to take into account and understand the periodic table. So let me stop share. All right, so I'm gonna stop share and I'm gonna go on it right here. Good. Right? So it's sodium, potassium. So it's sodium, potassium, and X. And they ask you whether or not X will react more vigorously than potassium with water. Now, if you're supposed to know periodic table and periodicity, you would know that as you go down the group, right? So as you go down groups, the reactivity increases as you go down groups. And that has to do with the overall ionization energy and all of that. Because as you go down groups, it is easier for you to form ions. Why? Because the atomic radius increases as you go down groups, right? The nuclear charge weakens because of the increase in shielding effect. So as a result of that, ions, the electrons in your outer shell are easily lost. You get me? So it's easy to form ions. So the reactivity going down the group increases. So as a result of that, what you realize happening, students, is that elements further down the group, right, tends to react more vigorously. So of course, for question 2AI, right, element X will indeed react more vigorously than K. All right, let's share back the screen and continue. We're going good so far. So far, so good. All right, it says, would the solution formed from the reaction of X with water be acidic or basic? Let's think about it. First of all, we have to understand where X is in the periodic table. Remember that X is on the left-hand side of the periodic table. What we know about the left-hand side? Metals are normally on the left-hand side of the periodic table. What do we know about the oxides of metals? If it's supposed to, let's write the reaction. Now, if X is in group 1, when it reacts with H2O, it's going to form X2O, right? Why? Because, of course, obviously, X will actually have the charge of plus. Oxygen is O2 minus. So you will change in their valency, the formula will be X2O. Now, if the formula is X2O, right? So it's X plus H2O to form X2O, right? Plus hydrogen. Now, all metals, oxides and hydroxides are basic. So it would be basic because it's a metal oxide. All right? Good. All right. So I'll explain that answer there. That the solution will be basic. Continuing. It says write the electronic configuration for magnesium. So write the electronic configuration down. Give me a second here. All right, so writing electronic configuration. And let's go through this. Of course, everybody's supposed to know how to write an electronic configuration. That's all? By now you're supposed to. Magnesium, let's for those who don't know how to write one, let's learn it right away. All right? So of course, magnesium is 12. That is the atomic number for neutral species. Right? 1 second here. Yeah. So for neutral species, the proton number, the atomic number, which is Z, is equal to the proton number. So basically, If the atomic number here is 12, the proton number is also 12. Also, for neutral species, the number of protons is equal to the number of electrons. So if this is 12 protons, this is 12 electrons. The octet rule teaches us how to do this. What we need to do, of course, is to what? Distribute electrons. The octet rule says the first shell can hold a maximum of 2. The second shell will actually hold a maximum of 8. Right? The third shell 8. Now, it's 12 electrons using the octet rule. So we distribute the first 2. We distribute the next 8. 2 plus 8 gives us 10. So the remainder is 2. So, of course, the electronic configuration is 282. Everybody in agreement with that? All right? We should be. Let's continue. Going full speed ahead. You know. Let's check on the chat. Everybody's good in the chat? Any questions? Any concerns? Good so far? Excellent. All right. Good. All right, Mr. Coleman. All right, Mr. Coleman. Mr. Coleman is here with us. Hey, Mr. Coleman. All right. So continuing. All right. It says right here, it says, based on the position, so let's share the screen. It says, based on the position of element Q, write the formula for its carbonate. So let's look again on element Q. So we're looking on element Q. So element Q, let's look carefully where element Q is, guys. Element Q is in group 2, right? Right in group 2. Look right there. So it's in group 2. Therefore, because it's in group 2, obviously the charge is 2 plus. That's all. Makes perfect sense. Because the group that you're in also justifies the charge. That is to say then, you being in group 2 is telling you that, okay, you will lose 2 electrons to become stable. Now it says, based on the position of Q in group 2, what's the formula, right, for its carbonate? Let's go ahead. Now remember that carbonate radical is CO3 2 minus, right? Now if Q in itself is Q2 plus, right, then obviously the overall formula would be QCO3, right? Everybody get that one? QCO3? So far, so good. QCO3. Give me 1 second here. All right, so it's QCO3. All right, let's go. So that's the equation that we would have there. Let's continue. Question C, it says sodium reacts with element Z to form a compound. State whether the compound is ionic or covalent and explain your answer. So what we need to do now is to look on the position of element Z. Let's look where element Z is. Let's look, let's go up. Element Z. So element Z is in group 6. What this means about element Z, let's go to the whiteboard, and it reacts with sodium. All right? So it reacts with sodium. Element Z. What does this mean about element Z? So element Z is in group 6. Right? Remember that the group that you're in, it's a representation of the number of valence electrons that you have. So basically, element Z in group 6 suggests to us that the valence electron is 6. That is to say, it has 6 electrons in its outer shell. Right? 6 electrons in its outer shell. All right, just fixing the camera, just don't mind that. Should be on shortly. All right, good. Is it here as yet? All right, so element Z being in group 6, it means that Z will actually gain 2 electrons. So the charge on Z will be Z2 minus. It also means that because Z is to the right of the periodic table, Z is actually a non-metal. Now it says to us that what would be the compound form when it reacts with sodium? Sodium is Na plus. When it reacts with Z2 minus, that is Na2Z. Now it is a metal and a non-metal reacting. What is that form of reaction? When we have a metal and a non-metal reacting. Obviously, that is ionic. reaction, right? Yes. So of course, a highly compound is expected to be formed. Everybody in agreement with me? You're clear like mud or you're clear like water? Which one? Talk to me now. We're all clear? So far, so good? All right, let's check. All right, wonderful, wonderful, wonderful. Let's go. All right, so moving on to our next question. Moving on to our next question. Remember to share the live. Remember to subscribe. All right, share. Remember to subscribe. All right. So we explain our answer. It says, write the electronic configuration of magnesium. We did that already, right? Based on the element Q, we did that also already, right? Element Z, we did that. So we're at D. D as in dog or D as in donkey. It says if 5 grams, let's take a look at this one. So it says if 5 grams of calcium nitrate are decomposed completely, right? Calculate the volume of nitrogen dioxide produced at RTP. So this is moles and moles and react moles. It's moles and solutions, moles and equation. And I want to pause here for a second, guys. And the reason why I want to pause is because one, me know say a lot of we don't love moles. And whenever university, moles is one of the hardest topics that you'll ever encounter. Luckily, HTS have probably one of the best method of explaining how to do moles. So you guys are a bit fortunate, but you can even be more fortunate, of course, if you join our program here. But let's just look at it. My students would have known how to work this based on the fact that we would have split up moles in different stages. One, looking at it on a unit basis, looking at it on a die basis, right? Kind of approach. And of course, modes and solution and modes and reaction. Now, this question is actually a modes and reaction. And I'm going to explain why I said that. All right, just take a look at the question just a bit. And then before we actually continue. All right, so let's go now. So let me stop sharing the screen so we can go to our whiteboard and we can explain what's going on, right? Shall we? Let us go. All right, good. So it's calcium nitrate, which is what? CaNO3 bracket 2, and it's decomposing. Nitrates tend to decompose into its oxides and nitrogen dioxide. So this should decompose into calcium oxide and NO2, right? Let's look on balancing equation here. We have 6 oxygen, 2 there. So we can actually have a 2 here. We can also have, do we need a 2 there though? Let's just look on the reaction. Someone tell me, do we need a 2? Do we? Can look at it. Let's balance it. So it's calcium oxide, right? 2 NO2. That's 2, 2 is 4. Put a 2 there, right? Let me try to put a 2 there. So that's 2 calcium, right? So that's 4 nitrogen, right there. Our balance 2, 3, 6. 4 2s. All right. I'm looking carefully at it. If it is actually balanced, doesn't look balanced as yet. All right. Figure it out. So I actually place those numbers on purpose so you guys can play around with it, right? To see if you guys know how to balance chemical equations. So we're looking on the decomposition of calcium nitrate. Anyone have an idea how we go by balancing this here? Quickly. Anybody? So just give you some time to figure that out. All right. Firstly, remember as I was telling you that nitrates decompose to give. So let's talk about the nitrate decomposition. So that's the first thing that we want to talk about. Just a second here. All right, so the nitrate decomposition, that's gonna give us nitrate decomposing to its oxide. All right, so let's write it out. Nitrate will decompose to its oxide, nitrous oxide, and oxygen, right? Except for sodium hydroxide or potassium hydroxide, which will now decompose to its nitrite and just oxygen. And that is because of the thermal stability of potassium and sodium, right? So what we actually have here is calcium oxide, nitrous oxide plus O2, right? So that was just a trick there to see if you guys remember. Now, in balancing now, right? Let's see what we can do here to actually balance the equation. So that's 2, 3, 6, 6 2s 12, 4 2s 8, 2 calcium. Yes, so this is actually balanced now. So this would be a balanced equation for the decomposition of nitrates, excluding sodium and potassium. Sodium and potassium will just decompose into its nitrite. So for example, if you have NaNO3, that's going to decompose into NaNO2 plus oxygen, right? Good. So the first thing that we want to do when we work in a mole question, guys, is to write the chemical equation, right? Because the chemical equation forms the foundation or the basis from which we'll work. Once we get the chemical equation out of the way, right, and we have the balance equation, then we're good to go. Let's go now. The next step that we'll take is to, as I always tell my students, to determine what is your known basis. Now, the known basis in your question is one for which there's a quantity given for. The question told us that we get 5 grams of calcium nitrate, which is CaNO3 bracket 2, right? And they want us to find the NO2, meaning that the volume, right? The volume of NO2 at RTP. So we know the basis. What we're gonna do now is to use this known quantity to find the number of moles. Because when we're doing equations, guys, right? Moles is the central node of calculation. So we need to find the number of moles into this. Now, this is a mass basis. My students at HTS would know that, okay, once we're now looking at a mass basis kind of thing, what we need to do is to consider the MRE, which is the mole relation equation. That is to say what quantity, right, is equated, right, or is equivalent to 1 mole of a substance. Now, for a mass basis, 1 mole of any substance is actually equal to the molar mass of the substance, or the RMM of the substance. The RMM was given as 164, right? Remember that it's dimensionless, so there's no unit to RMM. So it's 164, right? And of course, it was 5 grams. So it's 1 mole of calcium nitrate is equal to 164, therefore X mole is equal to 5 grams. So that would be what? 5 over 164. Let's calculate that. So it's 5 divided by 164, what we get? Plug that in the calculator for me. Let me plug it in mine, just the same. So that's 5. So that's 5 divided by 164, right? Which is 0.03 moles. 0.03 moles. So it's 0.03 moles of calcium nitrate. Next thing that we want to do now is to ask ourselves, what do we do with these moles? It's obvious. They want us to find what? NO2. The next thing that we want to do now, guys, is to what? Establish the mole ratio between calcium nitrate and NO2. It's a 2-to-1 mole ratio. See here? Oh, you know it's a 2-to-1 based on the stoichiometry. So the stoichiometry is basically the coefficient that is placed in front of the number. Well, in front of the compound, my bad. Right? So it is 2 to 4, which is the same thing as 1 to 2. So for every 1 mole of calcium nitrate that decomposes, it produces 2 moles of NO2. So it's 1 to 2. So if this here, 5 grams contains 0.03 moles of calcium nitrate, it's obvious then that the number of moles of NO2 will be 0.06 because it is twice it. Right? So therefore, X is equal to 0.06. So we get the number of moles of our unknown, which is the NO2. But what do we do next? Let's look carefully now. The next step that we need to do now is to find what? The volume. Excellent. What's the volume? Let's look at it. It's at RTP. We know that 1 mole of any substance at RTP, in this case NO2, is equal to 24 dm cubes. Therefore, 0.06 moles is equal to X dm cube. Cross multiply. Yes, you can do that here, right? So 0.06 times 24. Plug that in a calculator for me. What do we have? Right? What do we have? 0.06 times 24. Sorry. 1.44. That's what we have. 1.44 dm cube. Excellent. 3 marks. Everybody get that 50 marks? Feel like we get that? Let me see what's going on in the chat. All right, let's see what's going on in the chat. Hope we're all getting that 1.44. Jada. Also, Jada is here. Jada getting one. I hope this is my Jada from HTS. All right, Jada get 1.44. Excellent, Jada. That's a product of HTS. All right, excellent. Wonderful. Remember, it's not too late to join us. All right, it's not too late to tell a friend about the live. Hope we're all learning. Thumbs up if you're learning, everybody. Delano, you really need help? Well, this is the place to be, Delano, man. Sashana, get it? Anybody else get the 1.44? DM cube? Sashana, I see get it. I said Jada, get it. Anybody else? Delano, please to visit our office. Call us 202-6446. We're here to save lives. Just like how the hospital save lives. Yes, HTS is here to save lives. Don't worry, we save your grade, your academic life, and your holistic development. All right, let's just check the chat to ensure that everybody is good. We're following, we're learning. O'Neill, thumbs up. All right, excellent. So we're going to move on, of course. All right, let's go. All right. All right, so how you feel about that 50 marks? So question 2 was worth 50 marks. You feel like you get 13 out of 50 because my students them cannot get anything below 13. You get anything below 13, you feel like we get the 13 out of the 15? What feel like? 13 out of the 15. So nothing shorter than the 13. If you feel like you get less than the 13, join HTS. All right, let's continue. Moving on. So that's question. So we're now on question 3. So question 3. So I hope you guys are understanding the dynamics of your paper by now. So the first 2 questions will come from module 1 or section A at the CSEC level, which is principles of chemistry. The next question, which is question 3, will actually come from organic chemistry, section B. Let's go. So we're teaching and going at the same time. Let's go. So it says organic molecules, right? Let's look at the question. Organic molecules can exist at different structural isomers, different term. Oh, sorry. Define the term structural isomer. What's a structural isomer? Anybody know? Someone, somebody? So of course, an isomer, right, is a substance that would contain the same molecular formula, but different structural formula. Just the same, a structural isomer is a molecule, right, that contains the same or that has the same molecular formula, meaning that the number of carbons and the number of hydrogens is the same, but overall arrangement and orientation is different. So for example, one can be in the straight line, one can be here, so one can be here, so one can be up here, so. But at the same time, they all have the same number of carbons and hydrogen. So let's define that again. So of course, a structural isomer, right? It's any organic molecule that have the same molecular formula, but different structural formula. All right, good. So 2 marks there. Let's move on. C4H10. So it says the molecule with the formula C4H10 can exist as structural isomer. In the space provided below, draw fully displayed structures of 2 isomers for C4H10. All right, let's stop share. Let's go. So it's C4H10. Let's just run through organic chemistry quickly. You think we can learn organic chemistry in seconds? Let's go. So of course, C4H10, this is an alkane. How do I know that? We have different homologous series, right? An homologous series is basically a family or a group of organic compounds. You have alkenes, right? Which is CnH2n. We have alkanes, which is CnH2n plus 2, right? We also have what? We have alkanoic acids, which is the same thing as carboxylic acids, right? Carboxylic acids, which is CnH2n plus 1 COOH, right? And by next year, you're supposed to learn, you're supposed to be learning this, right? Now, how we normally do this, we number carbon atoms from 1 to wherever, each based on the number of carbon atoms that you have, it's have a prefix. So if you have 1, that's met, just to revise for those who don't know. 2, it's F. 3, prop, right? 4, but. 5, pent. 6, X. 7, ect. 8, oct. 9, non. 10, dec. All right, good. So in this case now, this is butane, C4H10, butane. Now, how we normally do this? First thing that we want to do is to draw the actual molecule, the straight chain compound. So when we're performing isomers with this type of isomer, we can have branch isomer and we can also have straight chain isomer. Now, if we're supposed to draw this out as normal, then this is actually gonna look like this. So you have 4 carbon atoms in straight chain, right? With each carbon atom actually having 4 bonds. Why? Because carbons are tetravalent, meaning that they're supposed to have by right 4 species bonded to it, right? So it's 4 bonds. So this is butane. But we have a strategy that we normally use when we're doing isomers. Hear my strategy now. We have a brilliant man by the name of R groups, right? R groups. And R groups is CnH2n plus 1. CnH2n plus 1. First thing that we normally do when we're forming isomers, we manipulate the R groups. So we normally remove one of the carbons. So let us say that we have 4 carbon atoms in a straight chain, right? We go down by 1, meaning that let our straight chain not to have 4, but instead 3. And then that one that is removed will actually be added in such a way that the overall, right, when we're supposed to count in a straight line, the overall carbon atoms that we get is not 4, because it wouldn't be the isomer. But look what I'm going on. If it is a case on my side, when we go to come and remove this carbon atom, right, and I have this straight chain of 3, I'm going to put the C here. So if you realize, if I'm supposed to count this, it's 1, 2, 3, 4, it's still in straight chain. It's not branch, so it's definitely not an isomer. But if I'm supposed to move this carbon and put it right here, right, you realize then that my longest chain would actually contain 3 carbon atoms. Yes, ideally 3 carbon atoms, 1, 2, 3. If I'm supposed to number it from left to right, 1, 2, 3. If I'm supposed to number it from right to left, 1, 2, 3. If I'm supposed to number it 1, 2, 3. So the longest chain would contain what? 3 carbon atoms. So this basically defines structural isomer. Yes, they have the same 4 carbon atoms. However, the structure, the arrangement, rather, of the carbons differ. This one is in straight chain. This one is branch. We're all following? So far, so good. And of course, if we want to name this here, right, let's look at naming it. I would name it with number from left to right, right? And we look at the position of the R group or the branch group. So from left to right, this is the methyl group CH3, and it's on position 2, so it's 2-methyl, right? And we name the long chain, which is 3-prop. So it's 2-methyl propane, right? So that's 2 isomers. Excellent. Excellent. We're all learning? If I enjoy the live, give it a thumbs up. Give us some claps if I enjoy the live. Give us some comments if you feel like, you feel like you learned something, you feel like you need help, make we know what's going on. Or the chemistry are going so far, it's steamy, like H2O, but in gaseous form, or it's lukewarm like H2O in liquid form. Which one? If it's steamy, put H2O gaseous form for me. And if it's lukewarm, put H2O liquid form. Talk to me my side, quick and fast. Remember, so we have plenty more to go though, and limited time. But of course, you don't necessarily have limited communication with the HTS. You can join us. 4 months to go. We change lives in 2 weeks. What's going on in the comments before we move on? All right. We see Anton say it's steamy. All right. That is it. All right. Everybody say it's steamy. What do I say? Now, so my friend them on the live. What on? Them still not over Christmas yet? Somebody said there's no rest for the week. Don't wait until May to come in. All right, let's go. Back at it again. All right, so moving on. 4 marks, we get that there. Same question. Question 3, part B. So it says two hydrocarbons, right? Compound A and compound B shown below are gases at room temp, right? Let's look on them. So in compound A, let's just understand the fundamentals. Compound A, you realize that it actually have a double bond here, right? Which is suggests that it's an alkene. So if you don't know organic chemistry, you know that that alkenes have double bond. Functional group is C double bond C, right? And compound B now, as you can see, it's an alkane. Simple question I'm asking, man. So I said, describe briefly one test that can be used to distinguish between compound A and compound B. How can you use the, distinguish them? All right, so first of all, the mere fact, so let me stop here and we'll go to the board and we'll talk some chemistry. So we'll talk chemistry here. So alkenes, because it has a double bond, guys, it's actually very reactive as opposed to the saturated C to C bond. This is saturated because it's restricted. In this double bond here, you actually have what is known as delocalization. As you go up, for example, in cave chemistry, you learn about pi bonds. So this actually have pi bonds and sigma bonds, while this just have sigma bonds. So there's some form of rotation about the central node of axis here, while opposed to C, single bond C, there's no rotation, it's restricted, right? So C double bond C is more reactive. Now, our test for this, we can use what is known as bromine water, because the alkene will actually decolorize bromine water. Or you can use a known oxidant like potassium permanganate or your potassium. Sorry about that. Or your potassium dichromate, right? So you can use you can actually use either one. Let me just try to set back the camera here so all can see good. All right, I think everybody should be good here. All right, sorry about that. So of course, you can use bromine water. It's bromine water. And what is going to take place is going to move from brown to colorless. Right, brown to colorless. And if you use potassium permanganate, KMnO4, it's going to move from purple to colorless. All right, and if you use potassium dichromate, it's of course going to move from orange to green. All right, so that is your test. You can use an oxidant to test for it. All right, hope everybody is getting that. See what's going on in the live. All right, so we still have some persons here. All right, good. All right, let's back to it now. All right, it says both compound A and B burn in oxygen. Write a balanced chemical equation for the burning of compound B in excess oxygen. Now, the excess oxygen suggests that it is telling us that we have complete combustion taking. We have complete combustion taking place, right? We have complete combustion. Now, let me go to the whiteboard. So it's compound B, C3. Compound B is actually propane. Oh, we know that. Let's just look. So if it's 3 carbon atoms, singly bonded. So of course it's alkane. It belongs to the homologous series alkane, right? And compound A is propene because it's double bonded. It belongs, and it has 3 carbon atoms. It's an alkene. And it's propene. Let's now look at the reaction, however, of compound B, right? So write this equation down for me. For any given hydrocarbon, it's CXHY plus O2 oxygen, and it's normally form carbon dioxide and water, right? In this reaction here, it's C3H8, which is propane reacting with oxygen, and it's going to form carbon dioxide and water, right? It's going to give us 3 CO2 here, right, plus 4 H2O, right? And on this side, let's balance This is 5O2. All right, so that's 5O2. All right, so this is CX. So this is the general formula, CXHY, right? XCO2, right? CO2 over 4. This is X plus Y over 4 O2. So this is a general formula, right? Y over 2. So as you can see, if I'm supposed to have 3 here, so it will be 3, Y over 4, 8 over 4 is 2, 3 plus 2 is 5. That's why I get the 5. X here is 3, so it's 3 CO2, X CO2. Y over 2, so it's 8 over 2, which is 4. That's why I get that. All right? All right, good. All right, good, 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 good. All right, so let's go back to our question. Hope you guys enjoying so far. All right, it says, give one use of each of the following. It says, one use of compound A. So compound A is an alkene. Anybody know what we use alkenes for? Anybody, somebody? So it can be used in a lot of things like fuel, right? It can also be used in plastics, like polypropylene is plastic bag, right? So it can be used, compound A can be used in plastics. One use of compound B, compound B can also be used as fuel. That's why you have like E10, right? Gases when you go to the gas station, things like that, right? Let's look on question C now. All right, so it says compound A reacts with X, right, in the presence of sulfuric acid at 170 degrees Celsius to form compound B. It says identify X. Let's look carefully. So it says identify X. All right, so this is a type of reaction which is known as the hydration. So it's hydration of alkenes. So alkenes will actually react with steam, right? So let's look on the reaction on my whiteboard. So alkenes, right? So alkenes, this alkene here. All right, let's look. It's react with X. So it's react with steam, just H2 in gaseous form to actually form alcohols. And the sulfuric acid will actually be acting as a catalyst in the overall reaction. So that is what is actually taking place there, right? So it forms alcohol, right? And the process is known as hydration. So it's hydration of alkenes, alkenes. So what you realize, you're learning while you're going around the way. That's good. All right. Part 2, it says state the name of compound B and the homologous series to which it belongs. How would we name this? So naming of compounds. All right, so let's look at it. Let's stop here. So this is our compound. This is our compound here. You realize that it actually have an OH group. The OH group signifies that, of course, it's an alcohol. It's on the second carbon atom. It's 3 carbon atoms that's there. So the prefix is what? It's pro, right? OH signifies that's an alcohol, so the name ending or the suffix is anol, right? The OH group is on the second carbon atom, so we call it propan 2-ol, or we can call it 2-propanol to be specific. All right. Hope everybody get that. Let's see what's going on in the chat. All right, going on good so far. Excellent. All right, so let's share back. I have around 10 minutes to wrap up with you guys. I wish I could stay longer, but of course you can get me longer. If you want, just join HTS. All right, let's go. So we're on now question 4. Now question 4, which normally comes in section B of the past paper, not on the syllabus now. So question 4 is actually from section A of the syllabus. All right. So remember, your first 2 questions comes from section A, the 3rd question from section B, the 4th question from section A, 5th question from section B, and the last question come from section C. All right, good. Let's go. So it says magnesium and sulfur are 2 elements in the same period of the periodic table. The oxides of these elements show different positions as presented in table 2. And let's take a look at table 2. All right. It says, with reference to the bonding, account for the difference in the states and the melting point of the oxides of magnesium and sulfur. What is the big difference? So first of all, let's look on the melting point. So obviously the melting point of magnesium is way higher. The magnesium oxide is way higher than sulfur, right? Sulfur is in the negative. State symbol for the magnesium oxide is solid. State symbol for the sulfur is actually gas. Let's talk about this. Now, magnesium is actually a metal. Sulfur is a non-metal. The oxide of magnesium, guys, is therefore what? It's ionic in nature, while the oxide of sulfur is actually non-metallic in nature. So therefore, sulfur dioxide that will be formed, SO2, is actually a covalent compound, as opposed to magnesium oxide, which is a what? An ionic compound. Let's not talk about it now. Magnesium oxide being an ionic compound, which is formed as a result of the electrostatic force of attraction between the positive magnesium cation and the negative oxide, right? The negative anion from oxygen, right? Now, in magnesium oxide, we actually have what is known as an ionic lattice. It is really a 3-dimensional array of repeating units, the magnesium ion and the oxygen interacting together. Now, because of that, it allows then for the ionic compound to be strongly held towards each other, right? Because you have one part negative being the oxygen and one part positive being the magnesium. So there's a great electrostatic pull, right? That is actually there, or a great electrostatic bond that is actually there. It therefore means then that if you are to, say, for example, separate them, or let us look on the melting point, it's going to take a large amount of energy to actually pull the magnesium away from the oxygen. Why? Because it's like a magnet, North Pole connected to the South Pole. You have some amount of electrostatic attraction or interionic strength, as opposed to the sulfur oxide. It's not necessarily transfer of electrons that is taking place, but it's more so now it's the sharing of electrons, right? Or the sharing of nuclei. Because you know of the sharing of nuclei, you can actually separate them easily from each other, right? And as a result of that, you don't necessarily require a great amount of energy, as opposed to You don't necessarily require a great amount of energy, guys, as opposed to in the magnesium oxide, which is ionic in nature. Everybody understand? 6 marks there. Confident that we get that 6 marks? Feel as if we get it? What's going on in the chat? Let's see. All right. Let's move on to the next question. So the next question, I think this probably our last question. I'm not going to finish the paper, as you can see, as we're running out of time. But don't worry, we'll talk afterwards, right? So it says, explain whether the oxide will conduct electricity, and if so, under what condition? So magnesium oxide, what do we know about ionic compounds, guys? Ionic compounds tend to do what? They conduct electricity in molten or aqueous state, because in those states, right? In those states, the ions are basically be able to be dissolute, or what we would say to disassociate. That is to say, then, let's look. Let me go to the whiteboard. So when we actually have water, this is what is taking place. So we're supposed to have magnesium ions, magnesium oxide. When it reacts with water, H2O, H2 is actually V-shaped in nature. Magnesium is positively charged and oxygen is negatively charged. Now, because magnesium is positively charged, the water is going to surround it in such a way that the negative pole on the water, right, attracts to the magnesium, right, while the positive pole on the water is attracted to the oxygen. Now, the water is going to now surround them just like this orientation, opposite attracts, remember? Right? And in such a way that this bond here, which is the ionic bond, becomes weaker. So basically, they're going to separate. That is why now, when they separate, you would have magnesium ions, Mg2 plus, and oxide ions, O2 minus, right? Being in the solution. Remember, let's use physics. So basically using physics to solve stuff. Let's look at it now. Remember, what is charge? Charge is Q equal IT, right? And electricity is the flow of charges. Now, if we're now supposed to now have these charges in solution, then of course and obviously we would have a current. You understand me? Q equal IT, we have charges, right? I therefore is equal to Q over T. We have charges. So it's now the flow of charge over a unit time. And hence we would have current. What I just did, I used physics to prove chemistry. Everybody follow it? So ionic compounds will conduct electricity in molten or aqueous state. Let me know if we're all following. All right. Let's go to the next question. All right, let's just, our aim is, we're gonna just aim to finish this question. All right, that's our aim, to just finish question 4. All right, let's look on this. So it says figure 5 is a diagram of the apparatus proposed by a group of students, right? If so, under what? Oh, sorry. It's a diagram of apparatus proposed by a group of students to investigate whether aqueous lead nitrate, ethanol, and aqueous ammonia conduct electricity. So it's electrolysis. First question, it says, why is the circuit as presented in figure 5 not suitable to achieve the aim of the experiment? Why is it not suitable? First of all, it's electrolysis. A lot of things are missing. Yes, you have the electrodes, which are these two pieces of rods or metals, but you don't have something to conduct the electricity, which is your electrolyte. You don't have a beaker at the bottom, right, to actually conduct electricity. You also don't have a light bulb that is connected to actually see then the intensity of the light, because only so you would know which one is a better electrolyte, right? So we explain why it's not connected properly. It says modify the diagram to produce a circuit that is suitable. All right, let's do that. So look on the whiteboard for me carefully. All right, so let's go. All right, so we're gonna modify it. So what would have? Still have the switch. Still have the switch. I have the electrode. So I have the switch. I have the electrode. I have our electrolyte, right? In solution. I have the switch here. I will also have our light bulb or our ammeter. So this is what is going to represent and tell us that, okay, you know, when we put in HCl, we see that the light was bright. When we put in something like a weak base like ammonia, it was dull, which suggests then that more current is produced when we use HCl. Why? Because HCl is a strong acid, so it's going to disassociate completely and produce greater concentration of H plus ions, which will of course cause greater conduction of current, right? So this is how we would set up our apparatus. All right, everybody follow that? Good, I think so. All right, last question now. It says classify the 3 substances to investigate, right? Aqueous, lead nitrate, ethanol, and ammonia, either as conductors or non-conductors. So firstly, conductors. Ionic compounds are conductors, right? So that would be lead nitrate. Ammonia is also a conductor, as well. It's a weak conductor, right? And ethanol is actually a non-conductor. Ethanol cannot conduct electricity, right? So we should know that. But that is it for our session today. So we would have completed, well, we have 2 questions left, which is question 5 and 6. But there's a strategy that I always tell my students, right? If you aim to really finish and to score high in questions 1 to 4, right? And you double in question 5 and 6, then you're on your way. But that's not what we want. But of course, you can get everything under one umbrella right here, right? To ensure that you get high score on all 6 questions, right? Proven track record here at HTS, right? You can go ahead and subscribe to our YouTube channel, follow us on IG, you know, and follow based on what we'll be doing, whether it may be free marathons again or any marathons, because we're now entering a marathon series in January, right? Which will have marathons every Sunday, right? So if you're interested, or mommy or daddy is interested, or you interested, tell mommy about the class. I hope it was a good session for you all. Let me know, let me see the comments, right? Let me know, let me see the comments, guys. Have yourself a wonderful time. And also remember that the live will be up on the YouTube channel, so you can actually be there. You can actually view and go through this past paper again. And remember that we continue our live sessions again on Tuesday, so the live will actually be up. All right, so you can always go and watch. All right, guys, you take care. All right, thanks, Jada. Take care.